Let's write some inline assembly code to calculate the area of a circle. Here is the main function, which starts off by prompting the user to enter the radius, and it computes the area of the circle for the radius entered by the user in two ways. One is by calling the C++ routine for computing the area, and the second function that it calls is calculate area asm, which is the inline assembly routine. So if you scroll down to the inline assembly routine, you'll see that right now I've left it blank. This is what we are going to fill out in the video. And the advantage of having a C++ routine which computes the area is it's easier for us to validate if the area returned by our inline assembly routine matches the area returned by the C++ routine. So it's easier to verify if our assembly routine is doing the right thing or not. So let's start by writing some inline assembly code here. We first need to specify the output list and the input list, and the way you do that while you're using the extended assembly format is by using a set of colons. So the first colon that you see in the list will be the output list, and the second one will be the input list. Usually the extended ASM format also has a third colon, which is called the changed registers list. We won't be getting into those details in this video. For this particular video, we don't really need to specify anything in the changed register list, so we'll just stick to having the output list and the input list. Let's start by filling out the input list. It's obvious that the input is the variable radius, and we add an identifier here called m, which basically means that the input variable radius is going to come from memory. The second thing we are going to do is to fill out the output list, and again the variable that has the output is going to be area. And the way I'm going to write this program is the area is going to be computed, and it's going to, the final area is going to reside on the top of the FPU stack. The top of the FPU stack is denoted by ST0, and here the shorthand which is used is T, and since it's an output, we prefix it with the equal to sign. So now that we have filled out the output and the input list, we are ready to write the actual code. So here I have a list of 4 steps that the code must do in order to compute the area of the circle. So the first step here says that we first load the radius on the floating point stack, and the way we do that is by using the floating point load instruction. And notice that our input variable radius is of type double, so we want to use the fldl version of the instruction. So then I specify %1 as the operand, and all that the %1 does is it's a placeholder which the extended ASM format provides to reference the input and the output variables. Notice that we put the input and the output, we've already filled out the input and the output variable list, so the placeholder of %1 merely denotes the second variable in the input output list. So the counting always begins with 0, so %0 would map to the area, and %1 would map to the radius variable. So the first step that we've done here is we have loaded the value of the variable radius onto the floating point stack, and I'm just going to document here what each of the instructions is doing so as to have a better understanding. So when I say TOS, it is short for top of stack, and the top of stack, as I said before, is denoted by ST0, and in this case at the completion of the floating point load instruction, it is loaded with the value of R. The next step is to compute the square of the radius. So we already have the value R, and now we have to compute R square. So there are two ways of doing it. I'll show you both ways. The first way is using the fmul instruction, and since it's a double variable, again I add a L suffix, and then I say %1 again. So what this does is it takes the value in the top of the stack, and it multiplies with the operand value. So the operand value is, again, since we have a placeholder of %1, it refers to our radius. So we already have radius in the top of the stack, and we use that radius and we multiply it with the operand again, and we get a value of R square. So that is equal to ST0, and that's R square. So that's the top of stack. Now at the completion of this instruction, the top of stack contains R square. The third step is to load the FPU stack with the pi value. So the x86 instruction set has this instruction called as fldpi, which loads the value of pi onto the floating point stack. Since there are no operands for this instruction, so we don't have to specify any. So let me write down here what happens at the completion of this instruction. At the completion of this instruction, the top of stack, or ST0, contains pi. Now what happens to the value that we computed before, which is R square? The value of R square now is in ST1, and for folks who are not familiar with this, I suggest they watch my video on understanding the floating point stack. So that should give you a better idea of how the floating point stack works. So in this case, all we have done is loaded a new value onto the top of the floating point stack pi, and the old value which was on the top of the stack has moved one place above the stack, which is denoted by the offset ST1. So now we have completed the third step here, which is to load the floating point stack with the value of pi, and all we are left to do now is to multiply R square with pi to get the area. So if you see the sequence of these instructions, now at the completion of the fldpi instruction, you see that ST0 has a value of pi and ST1 has a value of R square. So all that is required in this step is to multiply the value of ST0 with ST1, and that's exactly what we are going to do. So the fourth instruction in our sequence is going to be the fmul instruction, and this is we are going to just use the register version of the fmul instruction. So I start off by saying I want to multiply the contents of ST1 with the contents of ST0, and using this syntax where ST1 is before ST0, I guarantee that the result of the multiplication will be saved in ST0. So ST0 equals ST0 times ST1, which is pi times R square. So now at the completion of this instruction, we have the final result at the top of the floating point stack, and sure enough, the top of the floating point stack is the one that is mapped to our output variable area. So once the ASM routine completes, the top of the floating point stack winds up in the variable area, and the function returns the value of the variable area, and it returns to main. So I mentioned that there was one other way of doing the fmul in the second step, and I just want to briefly talk about that. So here you can see that I'm using the memory operand version of fmul, and all this is doing is it's saying that you multiply the top of the floating point stack fmul with the value in the memory location m, which is the radius. So you load a double precision value from the variable radius, and you multiply the top of the floating point stack with that. The other way of doing this is by observing that when we complete the first step, the floating point, which is the floating point load, the radius is already on top of the floating point stack. So if we want to multiply, compute r square, then an alternate way to do that would be just by using the register version of fmul, which is fmul st0 comma st0. So if you multiply the st0 with itself, you still get the same result, which is you're multiplying the radius with itself to get r square. So there are two alternate two ways of doing this. One of them is the memory version, and the other one is the register version. So let's try to build this program and make sure it works as expected. So going to the terminal here to make clean, and I build, I get an error here on line 45. Let's see. Oh yeah, I'm missing a new line here. Invalid as some operand number missing after letter. Operand number. Oh yeah. So the problem here is that when I use these instructions in the extended ASM format, I'm expected to use double percentage instead of a single percentage. I think that's the problem, and I don't think it matters whether I have a new line for the last instruction or not. And builds, and when I run the executable, I enter a value of 5 for the radius, and as you can see, the area returned by the C++ routine and the ASM routine matches, and this proves that the ASM routine works as expected.